Okay, that's where I wanted to begin. And I'll begin at the end of it. That dipole that you've got for 80 meters that you think is so cool because it's 30 or 40 feet up in the air is really an NVIS antenna because it's really not that high. But if you were going to do an NVIS, what you really want to be is even lower than that. And we'll get there in a few more slides. There's the credits I was giving because I don't want to do plagiarism. And there is the kind of the quick explanation. The guy in Arizona with the garden hose, which I think is just great. I thought about doing that. And then I thought again about doing that. There is Tennessee, and it's you see the explanation of what is needed. We are a hilly place, and a hilly place doesn't do that well everywhere for getting its signal into the lower areas within the state. That's kind of easy and obvious. Also, ground wave doesn't go that far, and Texas is quite a not Texas. Not my name. Lights are on, but nobody's home. Williamson County is a central location, but look, it's 200 miles or so to the southwest corner of the state in a straight line as the crow flies. And it's about 350 miles to the northeast end of the state. And ground wave doesn't cover that. Ground wave will cover this county and maybe two more beyond it, and that's about it. But NVIS does, which is why we're doing all of this sort of thing. A couple of important ideas, and I have to go through these like one by one on other slides, but one of which is, wouldn't it be great to have deep and intense coverage of Tennessee that you can do with your 100-watt transceiver and not worry about having to turn on the amplifier that someone is trying to sell. The downside of that is that you need to do this on a frequency that requires a general class license. If you are a technician class license, you've heard the announcement, this is a great time to become a general. Go out and do that because we're going to be talking mostly about 80 meters. We need to be below a critical frequency, and the critical frequency varies all the time. It can go up as high as 10 megahertz, but rarely goes above 8. And I'll talk about what the critical frequency means. Talk about the ionosphere, those layers that we have read about and maybe don't understand very well. We're going to talk about antenna elevation, low angle, what near vertical really means. It means a signal that way, which normally we don't care about. And rapid deployment of antennas, practical stuff like what Paul brought here and what I've got here on the table and others that I'll show. If we had a statewide or large area emergency situation to handle, and if the repeaters didn't cover it or went down, or if other things went down, what does not go down is near vertical incidence radiation. You've got to be prepared for it. And preparing for it means having the antennas ready. Critical frequency. There is a frequency all the time, and it varies, but it's a pretty low frequency, below which your signal straight up will come straight down. If you get higher than that critical frequency, it won't work. In tropical areas of the world, it could be as high as 12 megahertz. On a good day, it could be 10, but commonly it is between 2 and 8. So 80 meters at 3.9 megahertz is a really great choice of frequency. And what makes it work is the frequency that goes up and penetrates the D layer to the E or F layers. I'm going to get to that a little bit. And then comes straight down. The D layer is absorbent. But you penetrate it, get to the point where we're like back down from E or F. And you actually don't care whether it comes for E or F. That just has to do with a little bit of distance and stuff. But it goes up and comes down, and you don't know which layer it went and came back down from. And there's no good way to determine it. This is just a little graphic illustration of that. Penetrating the D layer up to the E and F layers. And yeah, that's big enough, you can read it. There's the E layer, it's about 70 miles up. It varies somewhat, but about 70 miles up. And there's the F layer, which is about 160 miles up. It also varies. In daytime, the F layer splits in half into what they call F1 and F2. But there are layers that are pretty high, having the D layer as an obstacle on the way up and on the way down. So you want a frequency that is low enough to penetrate D, but not so high that it penetrates E and F and goes straight up. E and F are your long haul DXing kind of propagation layers. Look at that. If you went up at 85 degrees to the F layer, you come back down, what does that say? 28 miles away. Heck, that's within the repeater. But it goes out, they say 270 miles away. That almost goes to the edges of the state. And of course, it's going to refract at other angles too. But see how vertical that is? You need an antenna that will do that. And you need to have one that is deployable. 3.980, 3980 is the Tennessee traffic net frequency. Good choice of frequency to be able to use. You might want to think about designing an antenna for lower than that so it covers everything from 3.9 to 4. And I'll be showing that in a few moments too, so that you can go off in that frequency to another place. What you need to watch out for is other states are going to do the same thing. And over Virginia is at 3947. But to be in that range, 3.9 to 4 is like the golden spot. And other things will be there, especially in a busy environment if there's some kind of an emergency, but they'll be there. In the daytime, it's not going to become a band longer than that. At night, it can. But 3.9 to 4, high end of 80 meters, what we call 75. Hard for me as a CW guy to talk about 75. I don't go there very often. My antenna at home is cut for the low end of 80 meters. It's got an 8-to-1 SWR at 3980, and I can get there, but it's a struggle. But that's just me trying to be use a CW antenna for this sort of a thing. Then we get to the subject of antenna height. What makes NVIS work is high elevation angle. We talk about it as vertical. It's not going to be really vertical because it's not coming literally straight down, but it's going to be very, very high, as that previous graphic showed. A half-wave dipole, look at that, it's kind of orange. That's a good DXing antenna. A 75-meter dipole at a half a wavelength is 120, 130 feet in the air. Anybody have one of those? I don't know that there's, who does? You can leave. Yeah, if you have a half-wave dipole at a half-wave for 160, it's 260 feet. No, of height. No. Okay. But an 80-meter dipole at 130 feet would be really great. Mine's at about 40. Quarter wave dipole. Quarter wave dipole is the color that's magenta in here. You see, starting to get the vertical incident of it. That's still 60 feet up in the air. Anybody got one of those 60 feet in the air except for you? No, few and far between. But look, and so this graphic shows at different heights. And the one that really works out quite well is the blue one at 1/10 of a wavelength high. That's going to be 20 to 30 feet, depending on the frequency one you use at 80 meters. Remember, 80 meters is a big band. The wavelength changes a lot in a big band at a low frequency. A quarter wavelength at 75 meters at 60 feet, 20 feet is kind of pretty good for this. Similar to here, I don't know exactly how high this is all put up, but it looks like it's mostly 20 feet. Is that about 20 feet, I guess? 15, okay, guessing. You can get too low. Look at the one that's green here at 0.03 feet wavelength. It's not a bad NVIS antenna, but when you get too low, you start having trouble with the ground and the proximity of it. And you start having problems with your impedance getting really nutty when you get really, really low. But I think this is a great graphic that I was able to find and put up here. I didn't make it, but I enjoy it. Look at the blue one. 0.1 of a wavelength high, 1/10 of a wavelength high. It's a great spot for an NVIS antenna to be. I did a little bit of modeling on EasyNet. I just want to point out a couple of things from this. The left is where I modeled the wire. I had made an inverted B dipole with 60 feet wire on each side. It says 57 or 58.75 because it's coming down. So that represents the horizontal line and down to 10 feet, the hypotenuse of that triangle. Excuse me. And you'll see that I put the centers at 20 feet and the ends at 10 feet. Very easy to put up something like that and support it. The other side is kind of the SWR curve with 50 ohm coax feeding it. And you'll find that for 30.9, it's a little bit, raises up a little bit here. It goes down below 2 to 1. You're not going to get a really low SWR. But most of our radios don't care at 2 to 1 or less. If you want a tuner, put a tuner in there. But if you look at those little numbers, they're big enough to see them. There's 1.82 is the SWR at that point where I put the measurement, and it says 31 or something like that, 30.89 ohms. Now, just the simple calculation of that is 50 ohm coax divided by 30.89, so it's divided by 31. Do that number real quick in your head, and you get a number less than 2, right? 1.8. That's the simple way of doing that. You're not going to get better than that, than 30 ohms of the impedance of the antenna because it is so low. When I mentioned the antenna heights a little bit before, and you read up on how high should your dipole to be, they say ideally a half wavelength, 130 feet. Isn't that cool? To get your impedance right. I mean, it varies as height varies. And this is an example of that. It's going to get even lower if you get lower. I mean, let's take this again. The SWR is going to get higher because the impedance is going to get lower as you get lower. That 0.03 that I showed a slide ago is an example of that. So expect less than 2 to 1 SWR. Don't expect it to get better than that. But it's still pretty broad for going 3.9 to 4. And that's not a bad thing at all. 31 ohms. And there's the reactance there. You can see that. And then we can go to the next slide, which really shows radiation patterns. It's not circular, but it's close. It's within about 2 dBs of being circular. It does have a shape to it. Ideally, therefore, you want to not have to get weird and fussy about it, but run your wire on a north to south line, ideally, so the broad side is east and west across Tennessee. But you have that kind of a shape, and there's the vertical pattern along the x-axis, and you see how high that is. And look at this. At 45 degrees, you do it that way, it is 3 dB less than it would be 45 degrees away from vertical, less than it would be at true vertical. 3 dB is a half an S unit. The world does not turn on a half an S unit. So you could, hi, what's the matter? Oh, thank you. Quite like works. That way. Where are you? Oh, well, what am I going to do with it? You put it down. I'll give it back. Yes, I will have I shine it at you. At 45 degrees, that's only 3 dBs difference from vertical. I mean, this is really very good. You don't worry about that. And at 45 degrees, it's going to cover everything in Tennessee. So near vertical incidence does spread, and it spreads not dramatically. You needed to cover all of Tennessee on 80 meters, but you do the job for you. And here's just an example. This is not Tennessee, but I found this graphic and I thought this was really cool. It's centered on St. Louis, Missouri. The red thing in the middle, you see that's the wire running north and south. You can see that. And you can see the pattern. The purple dotted lines are the pattern of what it would look like on the E layer, and the blue lines are what it would look like on the F layer. When you're setting it up and it's coming down, you really don't know what layer is doing the job for you. But only to a limited extent do you care. You take in your mind and imagine that shifted a little to the southeast and laid on Tennessee, and you see that an NVIS antenna on 80 meters will cover Tennessee very, very well. And it will cover our neighboring states if we need to do that. Look how intense it would be over all of Kentucky and the northern halves of Mississippi, Alabama, and Georgia. I wish I could have shuffled this, but I don't have the graphic skill to shuffle it out of Tennessee, but your mind can do that for us. You can see what it would look like. That would make for a very intense signal situation. You get up there with that antenna and 100 watts, and everybody will hear you. What's more, they will hear you better if they're doing an NVIS antenna. But even if they're not, unless they got something very, very high on 80 meters, it tend to act like an NVIS antenna, not optimized, but it would tend to act like that. And you would get the result you wanted. Signal, it goes up, and it comes straight down, and it ignores the mountains because it flies over them anyway. And there you are within a fairly intense situation that covers Tennessee in a block-busting, bone-crushing way. I know I got a little excessive there. And Jack, way out there in Arkansas, he would hear you fine too. Hi, Jack. And it would look like this. An inverted V, fairly wide one, okay, fairly wide one. And the purple line or magenta line represents current flow, similar to what I talked about off-center bed dipoles before. High current in the middle, low current at the end. High voltage at the end, low current in the middle. But it would do that job really, really well. This is the graphic that came out when I measured this with the centers, with the lengths of the arms at a total of 120 feet, 60 feet each. And the center at 20 feet, the ends at 10 feet, a one-to-one current balun in there. You'll find yourself a little much more simple in life if you run a 1.1 current balun. I'm a great believer in baluns. 50 ohm coax to feed it, and run the coax straight down. Now, Paul's antenna is standing behind me. You see where the coax connects to it way up there. Run the coax straight down. Nothing weird and oblong. I haven't talked about, and I'm not going to branch beyond this, what's called common current in antenna feed lines. Common current is when the antenna transmits, but the feed line being a wire near it picks up current and flows it back into your radio, and it comes out with nasty SWR and feed line trouble. So just, use extra coax if that's what you got to do, and bring it straight down. This is the good sense of always taking your coax, unless you can't, take it straight at a 90-degree angle away from your antenna, and your life will be much, much simpler. I've had some bad experiences in their life before I learned about common current. Just take the coax straight down to the ground and run it off the way you got to go to. Okay. There it is again. Another great antenna for near vertical incidence is a full wave loop. I'm going to talk about that separately in a moment, but I just wanted to show it there. The models from that. We were talking about how you might have to go out on an emergency basis, set up an antenna like this, which puts us into field day mode. Field day is a great place to think about antennas. I like field day stations that have to set up antennas. And I know we come down here, we operate in the room and the antennas are up on the roof, and isn't that nice? But I like the idea of having to set up in another place like you might have to someday and get an antenna up and standing. With that, I like the idea of having a near vertical incidence inverted V made up with the stuff that you need to operate it and parked in your garage or somewhere. So that if the word comes out about you need to go to a certain place and set up, you're ready to go. Like this one that Paul's got right behind here. You set that up, carried it in here, put it up. That's a 40 meter, isn't it, Paul? But 46. But having that together, he's got a support, he's got a post, and it works out great. And we do similar to this every Tuesday morning after the breakfast out there at either Dyer or at Liberty Park. And let me get to that. Oh, let me stop for this one. You can always do an inverted V fan dipole. You can have more than one band on this. You might wonder why to have more than one band. When I was asked to do this presentation, I would say, well, what about 40? Well, 40 is great until the critical frequency drops below 7 megahertz, and then it doesn't matter anymore. That's why 80 is such a good band. It can drop below 80, but it doesn't do it often. Okay. There's our guest star, Paul. This is what happens on Tuesday mornings. And it's very, very simple. He's got a mount there on the left that holds a mast, and the mount is held down to the ground by driving a car tire over it and nailing it down. It works out really well. It's easy to do. Very portable. Pack that up, set it up somewhere else. And the way he raises his mast is you push it up and then you kind of screw it together and push it up some more and screw it together. And it is how high? It's 30 feet or something? Okay, the one we're using, okay. And that's a lot. You don't have to raise the mast like that all the way. And there are places that sell them. I know MFJ sells this sort of thing. DX Engineering sells this sort of thing. I think that TN07 guy down there in the, oh, there you are. I didn't know you were here. He sells these things. Or if you had to, you could make one. It'd be very easy to have something like this, put it up, there's your dipole attached to the top, the coax is dragging on down, tie off the ends. Usually out there at the Liberty Park, the ends are tied off to a ground stake, which of course is a trip hazard. But you could have something very easy that supports the ends and keeps them 10 feet off the ground and not have the trip hazard, which is probably great. It's going to set out and it's going to get dark and people are going to walk away looking for anything they've got to get, except over your antenna and down it comes. But it's very easy to do. There's nothing about NVIS that is complicated or difficult or expensive. Probably the most expensive thing is getting that one-to-one current balance in the middle. Really, of all the little bits and parts. But I thought we'd have a movie star here with Paul. Paul does real well with it. Another option. Hold on, let's skip this part. I went to the W4DXCC conference, as I always do in September every year, and they had an antenna set up. So I took these pictures outside. You can get these steel stakes that have this little blade at the bottom. You can just go to Lowe's and buy these things. They're very easy. Hammer them into the ground with a lock if you had to. And they're all sort of U-shaped. So set into that, you could put a pole that supports antenna. Hammer that into the ground anywhere. A couple of big cable ties around it, like a, get that up there. And now you've supported the center on a very simple, portable, cheap basis. Two more of those that are only 10 feet high with a piece of PVC pipe that you bought at Lowe's. And now you've got the ends where the insulators are supported. It's very easy, very portable. Let me go to the slide that I got ahead of myself on. A full wave loop is a great vertical incidence antenna. And the idea when you do a full wave loop, if you've never done this, is to enclose the maximum amount of area you can within the loop, which obviously, not obviously, but ideally means a circle. Now, making a circle out of wires and supporting that is very, very hard. You could do an octagon. You could do a hexagon. Most people don't get much bigger than a square. But to do an antenna like this, supported at 20 feet, you still need 4 supports and 4 ways to mount and raise your 4 supports. And you need about 360 feet of wire. And it's going to be fed at about 100 ohms. You can feed a one-to-one down under 100 ohms and still get that SWR that we were talking about with the inverted V. The only difficulty with this antenna is that it's much more work to get it standing, but it will work. I remember a field day when I was still on active duty, and I went out with Marines, and we did field day at Camp Lejeune, and these guys would think, "Oh, we got to have a tower and a beam because you got to work the West Coast people." Oh, and they had all this trouble, and they got it up, and they were standing. And I stuck up a full wave loop, and I did more work on CW with that than they did with that other stuff. They put up with so much trouble. A full wave loop is a great antenna, it really is. But it is a lot more work than an inverted V, which is really the ideal with NVIS antenna. Vertical antennas that are mounted off of vertical. And when we had the program here on Hoka, Jeff brought one of these. Probably remember this. This was called the new super antenna. It comes with a base like this that can be mounted to a pole with a clamp. It can be mounted to a picnic table with a clamp like this. It has a spike that you can stick it into the ground. Very, very many options. The only problem with doing that is that the weight is, let me see if I can hold this here. The weight is obviously not balanced. And you really need to do this with the clamp. It will do NVIS in a direction. I tried to put this up here and I found out these rubber bumpers on the tables we've got are just too big for the clamp to work. But most picnic tables out there would be fine. You lean it at 45 degrees, you get NVIS on the opposite side of the way it's leaning. You can see that on the graphic on the right. So if directionality wasn't a consideration to you, it would make a pretty good NVIS antenna and very portable. Again, very, very, very portable. The point is, you can do this stuff. You can do this with your home station. You could make up one of these things that you've got ready to go as a go kit kind of item and stuff that would support it, and go out and be ready for this and do a strong NVIS signal throughout Tennessee and nearby states. So in that sense, it's great stuff and always be ready to go. And that kind of thing is what I wanted to say.